I'm leading this group, and this is one of our facilities where we can produce synthetic filaments. So this is a bicomponent melt spinning plant. What does that mean? First, let me tell a story about the development we did with respect to melt spinning of bicomponent fibers. And this is a topic which is at the moment very relevant. So turf, artificial turf for soccer, playing football. So why was there a need? So this is a product now produced by a company nearby. And let's start with a problem. The first artificial turfs were produced from polyamide. Polyamide is a polymer which, for example, is used to spin fibers which are used for toothbrushes. And they are used for toothbrushes because when they're made out of polyamide, you can use the toothbrush for a month, maybe even more, and it's still, the fibers still stand straight. And you also want the same to be true for artificial turf. You don't want the material to lay flat, otherwise the ball would roll very fast, it would not look nice. So you want to have straight fibers. But the problem about polyamide is when you slide on a carpet made out of polyamide, you get heavy skin burns. It's a problem of polyamide. So that's why people started to go away from polyamide for artificial turfs and went to polyethylene, another material which is softer, which is kind of a soapy surface, and it's much more skin friendly. You can give it a rod and try it. So this is a polyethylene surface. However, when you would make a toothbrush out of polyethylene fibers, you could use it one day and then it's already laying flat. What did people do to prevent that problem? They do infills in the artificial turf, sand or granules or rubber from tires which is grinded. So things you don't really want to have in your artificial turf. That's why with the company I talked about, we started a project where we wanted to combine the two properties of polyamide and polyethylene in one fiber. And actually then you would take a microscope and look at these filaments, how they look like. They have such a cross-section. Meaning we have several cores of polyamide, which give the resilience, so the ability to stand up after having been bent. And we have the sheath out of polyethylene, which gives the skin friendliness. With that, we could solve the problem, and this turf actually works without infill of granules or sand or anything. This is actually in use and sells quite well since more than 10 years. So a very successful project we did together with this industry partner. How can we achieve such fibers? So what we first need, we need to melt the polymer and pressurize it. For that, we use an extruder, which is kind of a tube which we can heat from outside, either with oil or with electricity. And then in the tube, we have a screw, with special design. The screw turns, and by turning, we transport the polymer within the tube. The polymer melts, and since the area, or the volume that the polymer has within this screw and the tube gets smaller and smaller, we also pressurize the polymer. So in the end, we have a polymer melt under high pressure. And we are talking here about pressures that in the end we have over the Spinnerei of 50 to 150 bars, so really high pressures. Then we have the molten polymer, and we can press it through a so-called Spinnerei, which in that case is just one polymer, coming from one extruder, which we finally press through such a spinnerei. And here we have 48 filaments, and you can look through, and then you see, when you look against the light, you can see very, very fine holes. That will press the polymer melt through. And then you have to solidify the melt. It becomes hard again, and then we process it further, which I will tell you later. But now the speciality about this, as said, what we can do here is bicomponent. That's the example of the artificial turf, the bicomponent. For that we need, of course, 2 of these extruders, as you can see on this picture. So we have one material coming, for example, from the side. So this is 2 times the same spinnerei. Here just cut in half, and we can see we have one material coming from the side, which then fills the annulus, and then we have another material which goes into the center, into the core. And in the end, this is a blow-up of the spinnerei, where we have then the core material and the sheath material processed together to form a filament. And actually these 2 extruders you can see at the top there, so right and left. And as said, the 2 polymer melts meet at the spinnerei and then are extruded and cooled and solidified. A filament we get right after the spinnerei might look like that when it's solidified. Now, when we draw, we see a strong plastic deformation. But what we actually want to have is a material which is not deformable, but elastic. And as you can see, after having drawn this, we have an elastic and relatively strong material. So the drawing is, after the extrusion, the drawing is also something very important. So turning the plastic material to an elastic material. So on the molecular level, that means we do align the polymer chains, the very long polymer chains, all in the direction of the filament. And this gives us the elasticity and the high tensile strength. To achieve this drawing in an online process, because in the end such a fiber is produced at speeds from 1,000 to 4,000 meters a minute, we have to do this drawing online during production. And for that, and when you look here, you see these shiny cylinders. They are so-called goddets that are heated cylinders from the inside, and they can turn at speeds of our choice. Meaning, when we go from the spinnerei first through a so-called quenching chamber, where we cool the polymer with cold air, then it solidifies, and then we start to draw it, and we do that by winding them around these moving cylinders. And when, for example, the first take-up cylinder has a speed of, let's say, 500 meters a minute, and the last cylinder of 2,000 meters a minute, we have a drawing factor of 4. So just by adjusting the speeds, we can decide how much we want to draw the fiber. And the more we draw it, the stiffer it gets, and with that we can decide about the tensile properties of a fiber. So apart from the extrusion, we also have the drawing, which is the drawdown unit, which is also very, very important. And as you can see, we have the possibility to easily modify the setups of the cylinders, the speeds, temperatures, everything. And this strongly depends on the polymer or polymer combinations we work with. So we have to be able to adapt the system to the demands of usually the polymer combination. So it's the polymer that tells us how it wants to be treated. So, and this is really when sometimes we also work with very new polymers which have just been or are in the process of being developed, or polymers with special additives. And then it always can take a long time to find the right parameters to be able to process a polymer into a fiber. So the fiber spinning is actually probably one of the most difficult ways to bring a polymer in a certain shape, because the requirements are really, really high that spinability is given. And our job often is to find the right parameters. It might take sometimes 2-3 weeks to find the right parameters to be able to spin a polymer into fiber. And when you think about combinations, like in bicomponent, it's even worse. Because then not only we have to be able to spin one polymer, but we have to find a processing window which fits to both polymers.
Can you combine a same polymer but with, for example, 2 or 3 different colors?
That's easy, yeah.
Okay.
Because that usually doesn't change the process parameters when you just add a color. So there you can even easily make, for example, 3 components. We could also do 3 components. It doesn't stop with bicomponent. But the problem usually is that the more components you have, the smaller the probability to find a processing window which fits to all. But as I said, when you just would change the colors, then 3 would even not be a problem. Because then we only need to find a process window for one of these, and then it also works for the others. Yeah. And that's actually also done when you look at the artificial turf. Maybe you don't see clearly, but actually these fibers have two colors. Yeah. Even the top floor has a different color. Yeah. So they have 2 colors in order that it looks more natural.
Yeah.
And that is actually done with 2 different extruders. So actually to produce this in one go, you need 3 extruders, not only 2. So 1 for the core, polyamide, and 2 for the sheaths, but with 2 different colors. Yeah. Yeah. Other possibilities are we can not only make artificial turf fibers. This, for example, is an example. Yeah, this is a polymer optical fiber. To produce polymer optical fibers, you also need 2 components. You need a core and a sheath. The core that is transparent, that is able to transport light, and the sheath that keeps the light in the fiber by so-called total internal reflection. And only with that way, and also a glass fiber, so this is a polymer optical fiber. Glass optical fibers always also have a coating which kind of keeps the light into the fiber. So with such a fiber, you can transport the light even when you bend the fiber. That's a specialty about optical fibers. You can see it, it comes out. But due to this total internal reflection, another effect is that light cannot be captured when it comes from the side. Whatever goes in goes out on the other side. But if you want to capture light, for example, if you want to have a big area, textile area, we want to collect the light and transport it to a solar cell, for example, at the end, we need to modify our optical fiber. We can do that, for example, when we use a special dye. This is a fluorescent dye, which we have in the core. And by using this dye, as you can see, we can actually collect light coming from the side, transport it within the optical fiber, and then collect it in the end. So with that, we can produce so-called solar collector. And as said, for that, we need the bicomponent technology. And we need very special polymers. And this is actually quite difficult, also demands a lot from the processes, from the machinery. The polymers are also very expensive. That's also why we never found a producer that wants to go in this direction. It's just too expensive. A fiber would be so expensive that it's very difficult at the moment to find an application. That can sometimes also happen. And to make things even more complicated, we also came up with something totally new, which is instead of doing a bicomponent fiber with 2 polymers, we developed a fiber which has a polymer sheath but a liquid core. So here you can see, just for demonstration, we produced hollow fibers, so fine fibers which just continuous hollow core, and then we filled it with red dyed water, just to show how fine this material is. Now, the question is, when you really want to produce fiber with a liquid core, continuous liquid core, could you not do it like that, make a hollow fiber, that's relatively easy, and then fill it afterwards with a liquid? Yes, you could, but even when you would think about 100 meters of such a fiber, to fill that afterwards with a liquid would take you several years. Years. Yeah. So even when you apply high pressure, it takes so much time to fill such fine, yeah. And we can do it, we can do 1 kilometer in less than a minute. And we do it by injecting the liquid directly in the spinneret. So similar like here, but of course we don't have an extruder, we need a high pressure syringe pump to inject the liquid. We developed a special spinneret to be able to do that. And by that, injecting it and keeping it in the core while the polymer solidifies, we get the continuous liquid core over several kilometers.